In these problems, we are finding the slopes of several secant lines to a curve to estimate the slope of a tangent. Why would you do such a thing? Well, this gets at something very essential about calculus, and that's called the derivative. So let's talk about that for a minute. Um, Here, I've got the line y equals x, and one of the chief pieces of information that we can get from a line is its slope, its rate of change. And that's a very useful thing because rates of change happen in all kinds of real world situations and we want to know them and predict them and so forth. On a line, the rate of change stays the same everywhere. In this case, it's going up one for every one it goes over. So it's got a slope of +1. And that's the case any point on this line. But if you had a slightly more complex function here, so let's make this y equals x squared. Now, what is the slope of this function? Well, it depends where you look at it, right? If you look just on the left half of the screen, it looks like it's going down, so that would be a negative slope. On the right half of the screen, the line's definitely going up, so that must be a positive slope. And presumably, somewhere between those two, the slope is 0 at some point because you can't go from a negative number to a positive number without passing through 0. So in curves, the slope is changing. To get a measure of the slope at any point on that curve, at some instant on that curve, is something that we call the derivative of a function. And it's kind of the first big thing in calculus is figuring out the derivative of a function. So you can know the rate of change of a function. How fast is this function changing at any point along its length? One of the ways that you can estimate a rate of change of a function is sketch what we call a tangent line to the curve. Just like a tangent line to the circle, you'd want it to just barely graze the function. And if you did that at the very bottom here at 0, you might think that we get a flat line here, a line with slope of 0. In fact, the x-axis really could be a tangent line here. It's instructive too to kind of zoom in on these because really on any curve, if you zoom in far enough and look at a small section of it, it starts to look pretty close to a flat line. So if I zoom in at 0 here, really close, basically at 0, you can see it's pretty much a flat line with a slope of 0. So drawing a tangent here, I would just draw a flat line with a slope of 0 and say that's what the slope is at that particular point. That's just eyeballing it though. So how do we really do that with accuracy and precision? What we're going to do is we're going to draw a series of secant lines and then make them get closer and closer to that point that you're looking at. I also typed in the function from this particular problem, so let me put that up here and we'll zoom back out. So we've got a gnarly looking function. Let me make this show up. There it is. Okay, so this is actually -6 times the cube root. I've got it to the 1/3 power because that's how we write it here in GeoGebra, but the cube root of x plus 2. And what the problem is telling us to do is to draw a series of secant lines to that point at -1, where x is -1, that get closer and closer to -1. They want us to um, draw a line that's from the point where x is -1.2 to where x is at -1, and then -1.1, and then -1.01, and then -1.001, and some numbers on the other side, all approaching closer and closer to that -1. So the basic idea is this. Let's see if we can do that. Need some tools here. So we're interested in the point where it's at x equals -1, so that's down here. It does look like it's at a value of 6 there, and we could easily calculate that too. I think that's correct, but let me put in a point here somewhere near that. So let's put a point right at -1, 6. There we go. So there's my point at -1, 6, and then I'm going to put another point somewhere out here. So it's close, but not very close. And if we were to make a line between those 2 points, we would have an approximation of a tangent line at A. It's not great, It's definitely not perfectly correct, but it's kind of close. You can see the slope's going to be negative there, and fairly steep. If, however, we were, whoops, I left the point tool on. Let me get rid of that. All right. If we were to move this point B closer and closer, you can see how the slope of the line is changing a little bit. It's the slope is getting more and more close to that, what the slope would be exactly at that tangent point. We can't actually get to that point. If you put B on top of A, the line doesn't exist anymore, so it winks out of existence there. But if you're really close, you're going to see a line that's very close to what the slope would be. So this is basically what we're doing in this project, but numerically. These points are getting closer and closer to -1. We're going to calculate the slopes, and if we see what the slopes are approaching, we can say that that's what the slope of the tangent line would be. That's the basic idea. In this problem here in ALEKS, they have a send to Excel function. I'm not using Excel, so I just did this. I brought in a bunch of all of those points that they want, all the X values, to a Google Sheets piece, and we'll do some work here. So what I want to do, I've got the X values, and what I want to do is calculate the Y values and then calculate the slope of a line between that point and the point -1, -6. So to calculate the Y values, I just really need to take the X value and put it into the original function, which is -6 times the cube root of X plus 2. So let's do that. With formulas, you need to start with an equal sign, and then you can just type them in the way you probably think you might. I'm going to do -6, use the asterisk for time. I'm going to put a set of parentheses here for the X plus 2, except I don't want X. I want the X value. So I just click on that, and it gives me the location of that cell A4. Now we're going to add our 2. So that's A4 plus 2 is really X plus 2. And we want the cube root of that. So this is going to be to the power of, and I'm going to put this in parentheses as well, so nothing gets confused here, 1 divided by 3. All right, if we did this right, it should say -6. -6 it is. And look what it did. While it suggested an autofill, I should have just taken that. If you click out of that like I did, you can just copy and paste down. All right, so now we've got all our values, and you can see starting at -1.2, we're at -5.5, then -5.79, then -5.9. We get really close to 6. The other way, we start at -0.8, we're at -6.3, then down to -6.19, then -6.01, then really, really close to -6. So we're definitely doing it right. We're approaching closer and closer to that -6. The only thing we have to do now is calculate the slopes at these places. It doesn't make sense. Well, actually, let's put the formula in here. So the formula for slope is the difference in the y coordinates divided by the difference in the x coordinates. So I'm putting a couple of sets of parentheses and then the division sign there, and it's going to be -6 minus our y, which is here, so B4, and then here it's going to be -1 minus our x, which is going to be there, and we'll just hit enter. Let's go ahead and autofill down. Now the very first one, we get a division by 0 error, which should make sense because we did -1 minus -1 there. So that's where the line disappeared when we put the points right on top of each other. But we should be able to see what the slope is approaching now. We're at -2.1, then -2.07, then -2.006, then -2.000. If we look at it from the other direction, we start out at -1.8, then -1.9, -1.99, -1.999. It's clear that from both sides, it is approaching a -2. The value of the slope is approaching -2. So all you'd have to do then is fill in the results you got for these things. And they want them 4 decimal places. So that's a little finicky, but you could do that. And then our slope here is going to be a -2. So that is how to estimate the slope of a line tangent to a function numerically by making a whole bunch of secant lines.